So let's talk about the initial rates method for determining the rate law. Okay, so how do we determine those reaction orders? How do we determine the rate constant? Common technique used in the lab is known as the initial rates method. So you do at least 2 runs, okay? You run the reaction at least twice. Keep all your initial concentrations the same for both runs, except for the reactant that you want to study. So, for example, here I have 2 experiments, reaction between A and B. In experiment 1, my concentration is 0.1 moles per liter of A and 0.2 moles of liter of B. In the second experiment, I changed my concentration of A to 0.2. I kept the concentration of B to 0.2. So which reactant am I trying to study in this experiment? Is it A or B? Am I trying to study the effect of A on the reaction rate, or am I trying to study the effect of B on the reaction rate? These are the initial concentrations for the experiments. 0.1 and 0.2 for A, 0.2 and 0.2 for B in both experiments. So what am I trying to study here? I'm trying to see what the effect of A would be, right? What happens if I double my A from 0.1 to 0.2? But for me to know that, I have to make sure everything else is constant. So that means I have to run this reaction at the same temperature, and I have to maintain the initial concentration of B in both runs. So that's how you design experiments using the initial rate method. Okay? This one requires a little critical thinking. Okay? Which pair of experiments allows us to determine the order of reaction with respect to reactant A? So experiments 1, 2, and 3. Which pair? 1 and 2, 1 and 3, or 2 and 3? Will allow us to study the effect of A on the reaction. So let's look at these cases here. You have 2 males, 4 males, 4 males. So you have stock solutions of A and B. You're mixing them, okay? And then 2 males of B, 2 males of B, 2 males of B in all 3 experiments. But then you have water. This is aqueous reaction. So A and B are mixed in water, okay? And then you have 6 mils of 6 mils of water in experiment 1 and 2, and 4 mils of water in experiment 3. Okay, popular answer is 1 and 2. Why 1 and 2? What happens between 1 and 2? Use twice as much A. You maintain the same amount of B, right? So does that work? You fell for my trap. Okay, if you want to see the effect of A, you have to maintain the concentration of everything else, right? You change the concentration of A. Sure, you've changed the concentration of A by changing the volume of A. But are you maintaining the concentration of B? You're using the same amount, but is the concentration of B the same? Look at the total volume of your mixture. This is 2 plus 2 plus 6. That's 10 mils, right? And here you have 4 plus 2 plus 6. That's 12 mils. You have the same amount of B, but the total volume is not the same. The concentration of B is not the same in both experiments. So A is wrong. Okay? So it's not A. So let's do a do-over. Let's pick between choices B and C. What's the total volume in C, by the way? 4 plus 2 plus 4. Total volume is 10 mils. Okay? Now, ready? Let's see how we're doing here. Very good. Correct answer is C. I mean B. Sorry. B. Why B? If you compare experiments 1 and 3, You have the same total volume, so the concentration of B in both cases will be the same. You're still changing the concentration of A, right? You're doubling the concentration of A, but you're maintaining the concentration of B. Okay. Here's some data you might get. Okay, let's say you have a reaction between A and B carried out in the lab. Okay, what's the order of reaction with respect to B based on the data shown below? So if I want to know the order of reaction with respect to B, what two experiments would I have to do? I have to change what? Concentration of B, right? So which one should I compare? 1 and 2 or 1 and 3? Or is it 2 and 3? Obviously not 2 and 3, right? 1 and 2? Why 1 and 2? Because you want to maintain the concentration of A in both cases, right? So, can you figure out what the order is just by looking without doing any calculation? What happened to the rate when I tripled my B without changing my A? Tripling B causes what to happen as far as rate goes. Has no effect on the reaction rate. So what is the order of the reaction based on reactant B? Zero order. Okay, so we say the rate is independent of B, right? So it's zero order with respect to B. Same data. What's the order of the reaction with respect to A now? So we know we've already seen that B doesn't matter what B is, right? We can ignore that. Can we just eyeball this and see what the effect of A is on the reaction? If I doubled my A, what happens to my rate? It doubles. Okay, experiment 1 and experiment 3, 0.1 to 0.2. I doubled my A, what happens to my rate? So what's the order of the reaction with respect to A? First order. First order. Okay, so I say that my rate is equal to K times concentration of A. All right. Okay. Now, let's try to do this more systematically because a lot of times you cannot just eyeball these things and figure out what the rate law is, right? So let's do it systematically. Let's go back to this problem right here. Here's what I would do if I were to systematically solve for this problem. Okay, because you're not always going to get those really nice numbers that you can easily tell what the result is. So what if I did this? I'm going to say then rate for experiment 1 equals K times A raised to the power. I'm just going to call little a the order with respect to A and little b the order with respect to B. Okay, so rate would be equal to, I'm going to say, K times concentration of A times concentration of B raised to little b. Okay? So according to this, rate 1, 0.050 moles per liter per second. So from experiment 1, I can say my rate is 0.05 moles per liter per second equals K times concentration of A is 0.1 raised to the power A. That's concentration of A. Concentration of B is 0.1 raise that to the power B. Okay? And what two experiments I need to compare? Experiment 1 and 2, right? So experiment 2 says 0.05 moles per liter per second equals K times concentration of A, which is 0.1 raised to the power A, times concentration of B, which is 0.3 raised to the power B. Okay? I have two equations, and I can solve for B, the order with respect to B. How do I solve for the order with respect to B? Everything else here is the same except for the concentration of B, right? So what I can do is I can divide equation 1 by equation 2. So experiment 1 over experiment 2. What is 0.5 over 0.05 over 0.05? That's 1, right? What happens if I divide the right side? K over K is 1. 0.1 raised to the power A over 0.1 raised to the power A is also 1, right? And what do I have here? What is this one? That is 0.10 over 0.30 raised to the power B. Okay, so that's equal to 1. So I can say then that 1 is equal to, what's 0.1 over 0.3? That's 1/3, right? 1/3 raised to the power B. So to what power should I raise 1/3 in order to get 1? 0. Okay. Therefore, B is equal to 0. Now, how are you going to use, if this wasn't some nice number like 1, this is obviously is equal to 1, right? But if this wasn't some nice round number, like let's say this was 0.9996, what would you have to do? You could say you can round it up to 1, but you can actually solve these things more systematically if you don't have nice round numbers. Okay, so let's do a little review of logarithms. Okay, so generally when you do these problems, you end up with an expression that might look something like this. Okay, so you might say 0.242 is equal to 0.489 raised to the x. So you're not going to get nice round numbers in a typical situation. Okay, how would I solve for x here? If you have an unknown in the exponent, how would you solve for that unknown? You do logarithms, okay? So you say 0.242 equals, what is it, 0.489 in this particular example, raised to the power x. So you take the log of both sides, so you say log of 0.242 equals the logarithm of 0.489 raised to the power x. Okay, review of logarithm. Log of a to the x is equal to what? I can move my x to the front. It's going to be equal to x times log of a. So I can say this is equal to, so log of 0.242 equals x times log of 0.489. Okay, so that's what you have right here. And now you can solve for x. You divide both sides by log of 0.489. Divide both sides by log of 0.489. And so that solves for x. And if you did this on your calculator, you might find something like 1.98. So if it's very close to a whole number, you round it up to a whole number. Okay. Typically, when you're doing these things, round up to the nearest half integer. So if you get something like 1.54, you round it to 1.5. Okay. Reaction orders are typically either whole numbers or half integers. So